Hi, this is Jeff Heaton. Welcome to Applications of Deep Learning with Washington University. This is Module 13, Other Neural Network Types. This is part 1 of that module for autoencoders. To begin, we'll go ahead and run the helpful functions that we always run at the beginning of each of these. So autoencoders are a topic for deep that were very important in the earlier part of deep neural networks and are still used quite commonly. An autoencoder is essentially automatic feature engineering. It figures out ways that inputs can be represented into the deep neural network. To do this, though, we're going to need a multi-output regression neural network. Normally, you have just one output for a regression neural network. However, you can have multi-regression outputs. In this case, we'll have a whole lot of outputs to our neural network. So let's see what that looks like, really. We'll start just with function approximation, which is a very common thing to do for neural networks. What we're going to do is we are going to approximate the input is going to essentially be a sine wave. And we will run this very basic neural network for it. If we run it, it begins to train. Function approximation is when you need to have a neural network with a single input approximate a function. Here we're going to teach it to approximate the sine function. It's using just a basic 3-layer neural network, and we're going to train it over the sine function and see how closely it can replicate it. Okay, training is complete. Let's see how well it did. These are the actual values for the sine over this. We're just printing out the first 5 rows here. But you can see it matches up pretty good. 0.00, 0.01, and you can see it's lining up. On the regression chart, now this is a regression chart where we don't sort because it looks better for the sine. We can see the sort of sine wave. The sine wave, even the expected, is a little bit bumpy because we're not uniformly sampling from the sine wave. We're not providing every single value. You can see it is somewhat overfit because it is following, and we didn't do any sort of early stop. So it's very much overfitting this, and it follows the kind of curvy, random samplings from the sine wave. But it is overall, it's a pretty good output. The goal here is not to produce a perfectly fit sine wave. The goal is to show how we can now use multi-output regression. So multi-output regression is just where you have multiple output neurons, almost like we have in classification, but instead we're trying to regress multiple values. So we're going to try to teach the neural network to predict sine and cosine both at the same time. So here we will do that. We are now passing in 2 values instead of 1. We have 2 inputs, sine and cosine. We're doing all the radian conversions that we expect there. And we are essentially, and we're randomly sampling them. We're taking 100 randomly sampled values from the sine. That's why it's kind of jerky, even on the expected. So we're going to go ahead and run this, and we will see the output of the 2 values that we're trying to simultaneously predict. Okay, and now we have the output. The RMSE is pretty good, 0.08. And you can see over here is the sine that we're predicting. And again, it's pretty well lined up. So is the cosine. Now the range that we're showing here is not really that creative for the cosine. We're at a crest, it looks like. So let's move this out just a little bit. So we'll start at position 20. And I don't know that I want to retrain it, so let's not run this entire cell. Let's insert a cell below, copy those, and let me move those back to what I had so that we don't. So if I run that, okay, this is a much better range of values because it's more interesting for both of them. You can see that the predicted and the expected are lining up a lot better. The 2.97, the 1.0, 0.9, 1.6. So this is a better range of values for both the sine and the cosine. In fact, I am just going to go ahead and paste that in and make that my actual example. So now we're going to look at a simple autoencoder. An autoencoder is a neural network that has potentially multiple hiddens, but it has input 1, 2, 3, 4, 5. The outputs match the inputs, and you can have any number of hidden layers. In some ways, this is the most boring network in the world because we are training the neural network to the x and the y are exactly the same. You're training the neural network to reproduce the x with the y, but the point is you have fewer hidden neurons than you have outputs. And by the way, this is a small typo. This should be hidden 1, hidden 2. But that's the simple auto-encoded neural network. So you're teaching it with this constrained number of neurons. Use 2 neurons to duplicate the rest of these. So it's teaching it to be a compression algorithm. You're compressing it down to 2 hidden neurons using a bunch of inputs and the same number of outputs. So let's look at this very simple example of a autoencoder. This, what it is doing is I am basically creating, let me print out X because that'll make it a little more obvious what's going on. So we print out X first. And that is what we're training on. We're teaching it to count to 10, 0 to 9. And it trains it to a very low RMSE. And notice the output is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Just like the input. We're teaching it to compress this down. We have 10 inputs, like we have here, as a result of this. This says that there's going to be 10 inputs. But we're using just 3 neurons to compress that down. So we're teaching it to go through that bottleneck and come back out without losing any detail. We're going to do this with much, much bigger inputs. We're going to use images, actually. First, let's see how to read images actually in Python. You'll use the pill library, and this was on the list of things that I had you install when you first installed Python. So if we run it, we'll see that basically this image that we have here, we're using an image of Brookings Hall from Washington University. And we print it out. You can see that basically you have RGB values, red, green, blue. And there's Brookings Hall. That's an older picture of Brookings Hall. It does not show the new landscaping or not construction actually that is being done in front of that. You can also create an image completely from scratch. So let me run this. Red, green, and blue, almost the Windows logo. And all I'm doing here is I am literally constructing this. I create width and height is 64 by 64. I create a matrix of zeros that's going to be height, width, and actually it's a cube by depth 3. So the yellow square, I am basically looping for row, column. It's 64 by 64, but I'm looping 32 by 32. So I'm just going to fill in this first part of it that's yellow. Then I fill in the red. I offset my my rows by 32, but do everything else the same. So now we're down here. And by the way, this is a red value, 255.00. So red, green, and blue, 0. Red and green makes yellow, so that's 0. And then 0 for the blue. Then we fill in the green. We're offsetting both the row and the column by 32. And the blue, we're offsetting only the column. And we basically, we created a whole bunch of numbers here and built up an image literally from scratch. That's a great power that we have. We can now create images and display them literally from scratch. And we're going to use the neural network output to create these images. We'll see that we can transform these images at the pixel level. So what we're doing here is we are essentially loading it in. And here, all I'm doing is I'm going across the rows and columns. T, which means temporary, is going to be I'm taking the mean. So I'm taking the mean of each of those RGB values. So up here, we had all these RGB values. Each one by one, I would be taking the mean of 11, 17, and 7. I take the mean of each RGB pixel, and I create a new RGB pixel where red, green, and blue are all the same. Now, if you've ever worked with images before, if the red, green, and blue value are all the same, it's a grayscale. So we're taking the entire image, taking the pixels, taking the average, and then blowing that out to the red, green, blue values. We're essentially taking the grayscale of the image that we have. So if we use that same Brookings Hall image, then we, it takes it a moment to run, we'll get the grayscale image of it. You can put in any image that you want to. I have a picture of me there from my website that I use just to test it with. So now we're going to do an autoencoder of just a single image. We're going to resize these images down to 128 by 128 just to make them a little more manageable. And we're going to create a 10 neuron hidden layer network that takes that entire image, and it's basically crunching it down that those 10 neurons learn how to encode that image just using those 10 neurons. So it becomes a very small encoding of it. 10 doesn't do particularly well with that. If we run it again, though, we get a slightly better rendering of it. So those 10, now this is not nearly as difficult for it as it might seem. It's 10 hidden neurons, but it only has one image to learn. So those 10 neurons can do this relatively easier. If you run it again, you get a different value. If you give it more training epochs, though, you'll get an even better rendition of that. Now there's very little distortion. But basically what we're doing is we're using that same technology where I built that 4-squared image. We're essentially just building an image array of all of the predictions coming out of the neural network, reshaping it so that it's a cube, and building up the image from it. So you're taking the input to the neural network was basically all of the pixels of that image just flattened out. And then the output, we get that same flattened out sort of thing, but we shape it back to a cube so that we can actually display it. So that was training on just one image. We can train on a bunch of images. I took pictures of, I didn't take them, but they're on Wikipedia. I took a variety of pictures of Washington University buildings because they look all relatively similar. They've got the I think it's called academic Gothic is the architectural style used here, but all of the images look similar but different. So it can learn some common compression techniques on them. First, we're going to see how to standardize these images, though. We're going to take all of the images and standardize them. We're going to make them square, perfectly square, height and width are the same. And we're going to shrink them all down to 128 by 128. So let's run this standardizer. It's going to need to download each of those images, which doesn't take too long. Now there's no distortion going on here at all. These are literally the images just as we got from MediaWiki. And it's this little bit of math that we're doing here is just centering the square cut of it so that we truly take a pretty good representation of the image as a square. So now we have all of those. We are going to do a multi-image autoencoder. And here we're encoding them down. We're using 100 input neurons because we've got more images going on. It's more difficult. And we basically set up exactly the same thing. We're going to encode them. We're going to flatten them and then encode them, send them to the neural network, train it using those 100 neurons to represent those. And then we're going to take it back out and display it as our cube. So now it is creating the neural network and training. Okay, now it's done. Now the difference here is this is one autoencoder that learned this for a variety of images. So that autoencoder is learning to represent Washington University type images. And it represents them pretty good. Definitely there's some distortion going on. If we take this down just to 10 input neurons, we give it much less to work with. And now it's training the neural network. You can see that didn't help at all. They're almost surreal looking. We could possibly give it more epochs to train with. Again, kind of the surreal looking images, but you can kind of distinctly see what it's doing. I mean, these definitely look like Washington U-esque surreal buildings, but those 10 neurons are just not enough. Maybe 50 might be enough. With the more epochs, 50 is actually pretty good. It's really representing them quite well with 50 neurons and using 1,000 training epochs. Again, there's no early stopping. I'm not really that worried as much about overfitting, but this is... So that's a good number. I will actually leave that as the class example. We can also use something called a denoising autoencoder. There's a variety of research on this. What this is really pretty interesting. Your x and y previously have been the same. You're teaching it with this x, always reproduce this y. Well, what you can do is you can add noise to the x, but not to the y, and you're essentially saying that even with this noisy x, I want this pure, perfect y. You're teaching it, given a type of input image, in this case, WashU academic Gothic style buildings, how do you take the noise out and repair the images? So it literally learns to repair them. So let's first see how we can just add noise to an image, just so that we can build our training set. So I'm going to, what it's basically doing is add noise. I'm creating a copy of the image so I don't destroy the original. I get my rows and columns, and I essentially create the size of 1/20th of the image. So this is the size of the random squares that I'm going to put into there. And then I put 100 random squares onto it. Now, the size of these squares are proportional, that's what this does, to the size of the image. So they're 1/20th. Let's go ahead and run this. We'll load in Brookings Hall, and you'll notice we're distorting it. We're putting squares all over it. Kind of ugly. But that will be the X. And then the Y that we're going to teach it is Brookings Hall with no distortion. And we're going to do that to all of the other images. So the denoising autoencoder, this just creates the data for it. So we're going to take all of those images, we're going to make them square, and then we're going to run the noiser on them. Actually, we're just loading them really at this point, and then train them. This autoencoder, though, is a 150-100, so it kind of sandwiches and then back out. Just a technique for creating a autoencoder that is hopefully pretty accurate at being able to denoise. And it's done. And we're now going to actually query the neural network, and we can see that we're giving it noise, and it's purifying the image. It's preparing to a very good degree, actually. This one it didn't do quite as well, but perhaps Graham Chapel looks a little different than some of the other ones. What's important to realize, too, about this is we added noise to the training set, but we are essentially going through this. So I do this for 10 images. These are all randomly generated. It would be a different set of noise each time. If I ran it again, it would be entirely different test data. So this is not the training data. This is completely out of sample. And it has learned to denoise these images. If we ran it again, it would be a whole new set of images to denoise. This is the end of this part of this module.